This video is going to be about entropy and how to calculate it. So entropy is a property of a system that is statistically related to the number of microstates that can characterize that system. So the more microstates, the higher the entropy. And that sounds very confusing and very complicated, and sometimes it can be, but basically what it's saying is if there's more motion and more possible configurations, then it has a higher entropy. So if we're comparing solid versus gas molecules have move more, they can collide with each other and expand to the volume of their container, while solids just simply vibrate in place. So there's more microstates with gases because they have more space available to them. And so therefore they have a larger entropy. You can think of entropy as disorder. The more chaotic a system, the more entropy the system contains. And if the entropy of the system decreases, the sign is negative. And if the entropy of the system increases, the sign is going to be positive for that. And the letter that we use to represent entropy is S. So this would be a negative S, and this would be a positive delta S. So particles in the solid phase will have a lower molar entropy than liquid, which will have a lower molar entropy than gases. More complex molecules have a higher molar entropy. So if we were to compare NO to let's say N2O4, this would have a higher molar entropy. Then this would have a lower molar entropy. Higher temperatures, this should be compounds at higher temperatures have higher molar entropy, so compounds here. And then lower pressures will give a higher molar entropy because there's less pressure on the molecules. And larger volumes will have a higher molar entropy. Okay, so is the entropy of the following systems positive or negative? So if we boil water, what we're really doing is we're taking liquid and we're turning it into gas. And so since liquid has a lower molar entropy and gas has a higher molar entropy, then that means the system is going to have a positive change in S. When we open a soda can, it releases gases into a bigger volume, and so this is also going to be increasing entropy. So it's going to be positive. And then here we have two aqueous ions forming a solid, so this is a precipitate being formed. So this is going to be negative because the motion is decreasing. And here we've got 2 moles of a gas, and we're forming 4 moles of a gas, one here and one here, so that's 4. And so that is an increasing entropy because we have more moles of gas, which lead to higher entropy. This is really important. All right, so which of the following pairs has the highest molar entropy? So if we compare gas to a solid, the gas is going to have a higher molar entropy. We have nitrogen gas at 25 degrees Celsius or nitrogen gas at 300. This will definitely be higher. Here we have, this is methanol liquid or ethanol liquid. Ethanol would have a higher molar entropy because there's more atoms. And then we have helium or argon. Well, these are both noble gases and they're both just atoms, but this is going to have more electrons and protons and stuff in it, so it's going to have a higher molar entropy. All right, so calculating the delta S for a reaction is the same way we calculated the enthalpy. The only difference is these are the molar entropy values, and before when we looked at enthalpy in these equations, they were the delta H of formations. So they were a change in enthalpy. Whereas here, this is an actual value for the substance. So elements like oxygen or even magnesium solid, they're going to have actual entropy values, unlike with the enthalpies of formation where they would be 0. All right, so they will have actual values. Now remember what this degree symbol means. It means that the values were measured under standard states. So if you remember back to gas laws, STP means standard temperature and pressure. Well, standard temperature for gas laws is 0 degrees Celsius and standard pressure is 1 atm. Well, a chemist doesn't want to work at 0 degrees Celsius, and we need to know what temperature these are being measured at. And so the temperature that we use for standard conditions, or sometimes you'll see standard states, is 25 degrees Celsius. And in thermodynamics, we do almost everything in Kelvin, just like in gas laws. So you might as well memorize 298 as well. That's just adding 273 to Celsius. All of the concentrations of any solution are measured at 1 molar, and any pressures are at 1 atm. So what I like to do when I work these problems is I like to look at the reaction and see if the entropy is increasing or decreasing, and then my sign should match it. And if it doesn't, then I've probably done something wrong. Okay, so here are all of the entropy values. And you can also get standard molar entropies in the table in the appendix from your textbook, but they have to be provided to you on the AP exam. All right, so for oxygen, the entropy value is right here, 205, and nitrogen dioxide is 240, nitrogen monoxide is 211, and ozone is 239. So to calculate that, we're going to take 205 plus 240 minus 211 plus 239. And that's going to equal -5 joules per Kelvin. So if we go up here and we compare these values, so if I compare oxygen to, let's say, ozone, ozone has a higher molar entropy because there's 3 oxygens instead of just 2. And if we compare NO and NO2, NO2 is more complex because it has an extra oxygen, so therefore its molar entropy is higher than NO. And if we look here, I've got 2 moles of gas on this side and 2 moles of gas on the product side, so it's not really increasing or decreasing, and that's why our value is kind of right next to 0. All right, so for B, the sulfuric acid aqueous solution is 20, and water is 70, and SO3 is 257. And that's something that I have forgotten to mention. The units for entropy is joules over Kelvin. It's not in kilojoules, it's in joules over the temperature. Okay, that doesn't mean just kidding, it means joules over Kelvin. All right, so for B, I'm going to take 20 minus 70 plus 257, and that's going to be equal to -307 joules per Kelvin. And that would be also, you could write per mole of reaction, because for this reaction to happen one time, I would have that entropy value. So if we go back and look at the reaction, here I've got a gas and a liquid, but then it's turning into aqueous solution. So since I have a gas that's turning into an aqueous solution, we expect the entropy to be decreasing. So we would get a negative entropy value, and that's exactly what we have down here. It's negative. All right, and then part C, I've got 193 for NH3 gas, 192 for nitrogen, and 131 for hydrogen. So I'm going to take 3 times 131 plus 192 minus 2 times 193. And I end up getting 199 joules per Kelvin per mole of reaction. All right, so if I look at my reaction, I've got 2 moles of gas here and 4 moles of gas here. So I should have increasing entropy, positive entropy, and it is.